Look at any ocean on a map: the Pacific, the Atlantic, the Indian Ocean. Together they hold 1.335 billion cubic kilometers of water. Scientists just published research suggesting that beneath your feet, buried 5,000 kilometers inside the Earth, there may be enough hydrogen to fill those oceans 50 times over. Not water, hydrogen. The building block of water, locked inside the iron core of our planet at pressures so extreme that the laws of chemistry work differently than they do at the surface. This wasn't discovered by drilling. We have never drilled more than 12 kilometers into the Earth. The core is 5,000 kilometers down. This was discovered in a laboratory in Switzerland by researchers who managed to recreate core conditions inside a diamond the size of a pinhead, and then look at individual atoms with a machine that most people don't know exists. If the findings hold, and the study was published in Nature Communications, one of the most rigorous peer-reviewed journals in science, then everything we thought we knew about where Earth's water came from needs to be rewritten. Let me show you what they found, how they found it, and why it changes the story of this planet from the beginning. Before we go underground, we need to understand the question this research is trying to answer. Where did Earth's water come from? This sounds like it should have an obvious answer. It doesn't. Here is the problem. When the solar system was young, roughly 4.6 billion years ago, the inner solar system, where Earth formed, was too hot for water to exist as a liquid or ice. The region where Earth formed was inside what scientists call the frost line, the boundary beyond which temperatures were cold enough for water ice to condense. Earth formed inside that line. In theory, it should have formed dry. Yet Earth has oceans, vast, deep, planet-spanning oceans that cover 71% of the surface. How for decades the leading answer was comets. Icy bodies from the outer solar system that bombarded the early Earth and delivered their frozen water cargo. It was a clean story, elegant even, but there was a problem. Comets carry water with a specific chemical signature, a ratio of regular hydrogen to a heavier isotope called deuterium. That ratio in comets doesn't match the ratio in Earth's oceans. Close, but not a match. Which means either comets weren't the primary source, or there was another source of water with a different signature that mixed with the comet delivery and changed the ratio. For years, that second source was unknown. The new research from ETH Zurich suggests it might be the one place we've never been able to look directly, the core itself. To understand why hydrogen might be hiding in the core, you need to understand what the core actually is. 5,150 kilometers beneath the surface. Earth's core is divided into two regions. The outer core, a vast ocean of liquid iron and nickel, roughly the size of Mars, churning in convection currents driven by heat and the planet's rotation. This is what generates Earth's magnetic field. The inner core, a solid iron-nickel sphere, approximately the size of the Moon, under pressures so extreme that even at temperatures above 5,000 degrees Celsius, the iron is forced into a solid crystalline structure. Inner core temp, approximately 6,000 degrees Celsius pressure, tilde 360 GPa depth, tilde 5,150 kilometers here, is where it gets interesting. Scientists have long known that iron alone doesn't fully account for the density of the core. The core is slightly less dense than pure iron should be at these pressures and temperatures. Something else is in there, mixed into the iron, reducing the overall density just enough to be detectable in seismic wave data, the only way we can indirectly probe the interior of the planet. The candidates have always included sulfur, oxygen, carbon, silicon. And hydrogen is the lightest element in the universe, even in small quantities, fractions of a percent by weight. It could significantly reduce the core's density while being nearly invisible in seismic readings. The question was whether hydrogen could actually survive there, whether it could be absorbed into the iron structure and held stable under those conditions. A team of geochemists just answered that question with a machine that fires lasers at diamonds. You cannot drill to the core. The deepest borehole ever made The Kola super-deep borehole in Russia, drilled over 24 years, reached 12.2 kilometers. The core is 5,150 kilometers down. Proportionally, if Earth were a basketball, the Kola borehole would be shallower than a scratch on the surface. So how do you study something you can never reach? You recreate it. The researchers at ETH Zurich used a device called a laser-heated diamond anvil cell. Two diamonds, some of the hardest material in nature, pressed face to face with a microscopic sample between them. Diamonds are used because they're hard enough to generate pressures equivalent to the Earth's core and transparent enough for a laser to shine through. The laser heats the sample. The diamonds squeeze it. Simulated pressure, ~111 GPa simulated temperature, ~4,800 degrees Celsius in that microscopic space between two diamond tips. They recreated conditions, 4,800 degrees Celsius and 111 gigapascals of pressure, matching what exists deep inside the Earth's core. Into that environment, they placed iron, silicon, and hydrogen, the elements thought to compose the core, and let them interact under those conditions. Then they looked at what happened, not with a regular microscope, with a technology called atom probe tomography. This machine, one of the most advanced analytical instruments in materials science, doesn't just image atoms. It identifies individual atoms one at a time by evaporating them from the sample and measuring their mass as they fly toward a detector. It produces a three-dimensional map of a material at the scale of individual atoms, identifying not just what elements are present, but exactly where each atom sits and which other atoms it is bonded to. The results surprised even the researchers running the experiment. When the researchers examined the iron-silicon-hydrogen mixture, after subjecting it to core-like conditions, the atom probe tomography showed something unexpected. Hydrogen wasn't just present in the sample, it had bonded to silicon in a remarkably consistent pattern. A 1-to-1 ratio. For every silicon atom in the material, one hydrogen atom sitting right beside it. This matters enormously. Silicon is already believed to be one of the light elements in Earth's core. Seismic data and density calculations suggest silicon is there in significant quantities. If hydrogen bonds to silicon in a 1-to-1 ratio under core conditions, and silicon is abundant in the core, then hydrogen would be abundant too. The researchers used this 1-to-1 bonding ratio, combined with estimates of silicon content in the core, to calculate how much hydrogen the core might hold. The result, 9 to 50 times the hydrogen content of all Earth's modern oceans combined. Range, 950 4T ocean hydrogen content, core weight fraction, ~0.07, 0.36% published, Nature Communications, 2026 confirmed. The 1-to-1 hydrogen-silicon ratio in the experiment is directly measured. Modeled, the extrapolation to 950 ocean equivalents depends on assumptions about silicon content in the core, which is itself estimated, not directly measured. Speculative whether this reservoir actively exchanges with surface water cycles is unknown. This is the frontier of the research. The wide range 9 to 50 reflects genuine uncertainty in how much silicon the core actually contains. The finding is real. The scale of it is an estimate within that uncertainty range. Both things are true simultaneously. Now here is what makes this finding so significant beyond just the numbers. If hydrogen exists in the core in these quantities, it had to get there somehow. And the most physically plausible explanation changes the entire story of Earth's formation. When the solar system was young, before the planets fully formed, there was a disk of gas and dust swirling around the young Sunday. That disk was rich in hydrogen, the most abundant element in the universe. As the material that would become Earth clumped together under gravity, a process called accretion, the hydrogen in that protoplanetary disk was incorporated directly into the growing proto-Earth, not just on the surface, into the interior. As the young Earth melted under the heat of its own formation, a period called the magma ocean phase. Dense iron sank toward the center. And hydrogen, bonding to silicon and iron as the new research shows it does under pressure, went with it. This means Earth may not have been born dry after all. It may have accreted hydrogen from the solar disk during formation, hydrogen that then sank into the core while some portion remained in the mantle and crust, eventually becoming part of the water cycle. Earth's water didn't need to be delivered entirely by comets. It may have been here from the very beginning, just hidden. This also potentially explains the deuterium ratio problem. If Earth's core-sourced hydrogen has a different deuterium ratio than comet water, mixing of these sources could produce the intermediate ratio we observe in Earth's oceans. Today, the comet delivery story isn't necessarily wrong. It may be incomplete. The core may be the missing chapter. Let's step back from the science for a moment and ask the obvious question. So what? Why does it matter where Earth's water came from? Why does it matter that hydrogen is in the core? Here is why it matters, at several different levels. If hydrogen was incorporated into rocky planets from the protoplanetary disk during formation, not delivered later by comets or asteroids, then water may be a natural outcome of planet formation in the habitable zone of any star, not a lucky accident of cosmic bombardment, a built-in feature. This changes the probability estimate for water-bearing planets in other solar systems, and with it, the probability of life. Scientists have long suspected that Earth has a deep water cycle. That water isn't just a surface phenomenon, but is continuously transported into the mantle through subducting tectonic plates and returned to the surface through volcanic eruptions. If hydrogen exists in the core in these quantities, the deep water cycle may extend all the way to the planet's center, a reservoir and source that operates on timescales of billions of years. The core is the least understood region of our own planet. We have mapped the surface of Mars in more detail than we understand Earth's interior. This research represents one of the first direct experimental windows into the chemistry of a place we can never visit. And what it shows is that the core is not just a ball of iron. It is an active, chemically complex reservoir that has been participating in Earth's story since the planet's first moments of existence. Before the payoff, let's be precise about what this research is and isn't, because the framing matters. Directly measured and confirmed hydrogen bonds to silicon in a 1-to-1 ratio under simulated core conditions. Published, peer-reviewed, reproducible in laboratory settings. Reasonable extrapolation, if this ratio holds in the actual core, and silicon content estimates are approximately correct, then 950 ocean equivalents of hydrogen is a plausible range. The 9 times lower bound requires the most conservative silicon estimates. The 50 times upper bound requires the higher estimates. Whether the hydrogen is evenly distributed or concentrated in specific regions, whether it plays any active role in surface water chemistry, whether similar reservoirs exist in other terrestrial planets. None of these are answered yet. This is not settled science. This is a significant new finding from a single study, rigorous, well-designed, published in a top journal, that will now be tested, challenged, replicated, and debated. That is how science works. And the finding is remarkable enough that it will be taken seriously. The headline, 50 oceans of hydrogen in Earth's core is technically possible within the uncertainty range. The conservative finding, at least 9 ocean equivalents, is already extraordinary. Either way, the core just became a great deal more interesting than it was a year ago. Here is what we know now that we didn't know before this research. The iron core at the center of this planet, the region we have never reached, never sampled, never directly observed, may contain more hydrogen than all the world's oceans combined. Not 9% more, not double, not 10 times, potentially 50 times more. That hydrogen got there during Earth's formation, absorbed from the protoplanetary disk and carried to the core as the young planet melted and differentiated. And that means Earth's water, the oceans, the rivers, the clouds, the water in your cells, may not have arrived on comets from the outer solar system. It may have been part of Earth from the very first moment it existed as a planet. We live on a planet whose surface we've mapped in extraordinary detail, whose history we've traced through fossils and geology, whose atmosphere we study in real time with thousands of sensors. And at the center of all of it, 5,150 kilometers beneath the ground you are standing on, there is a reservoir we've never touched, a chemistry we're only beginning to understand, and a story about where we came from that turns out to be far older and far stranger than we imagined. The most unexplored place on Earth isn't a jungle or an ocean trench. It is directly below you, and it has been keeping secrets for 4.6 billion years. If you want to understand how scientists piece together what the core looks like using nothing but earthquake waves, seismic tomography, how it works, and what it has shown us, that video is next. Subscribe so you don't miss it. I'll see you in the next one.